All right, so this is our next example. I gave you this polynomial, and I want to show that it has exactly two distinct real roots. So tell me how far you've gotten so far.
One of the roots is really easy in that if we plug in 0, we get a negative, and plug in 2, we get a positive. So location of roots theorem.
So 0 and 2 is what you want me to use? Let's see. So f of 0 is negative 9, and f of 2 is 16 plus 56 minus 9 is 63. So this one's negative and this one's positive.
So we know by the location of roots theorem that they're...
Before I use that, what should I do first?
Oh, it's a polynomial, so it's continuous and differentiable in there.
Right. So precisely, actually what we need is not differentiable. We just need the function to be continuous. Okay, so f is a polynomial, hence continuous actually on all of R. So in particular, any interval that I want to use, it will be continuous. Okay, so by location of roots, what were you saying, Joseph?
We know that there has to exist some root in between there.
Okay, what do you want to call it?
C.
Okay. In between there meaning?
0 and 2.
Uh-huh. And being a root means just that f of c is 0. Okay. Happy with that? Anybody else want to take over?
Or we could restrict
Somebody else. Somebody else take over. Anybody else have an idea? We've only found one root so far. I thought you guys have all these roots already figured out. F of 0 was negative 9. F of 2 was 63. Somewhere we have a root C right there. Is everybody just trying to do a whole bunch of mental math? Is that the idea here? For example, if you plug in negative 7, then you've got 7 to the 4th minus 7 to the 4th minus 9, still negative. So, what do I want to come up with here? Yeah, I want to choose an... See, you know it's a 4th degree polynomial with a positive first coefficient. So the general shape of a graph like that, hopefully you've seen in calculus, it's going to look something like that. So it eventually, if I go far enough to the left, has to go back up again. Okay, so what I did yesterday, and I'll do it again today, is I picked a number that is very easy to work with. Okay, 10,000 minus 7,000 minus 9 is definitely positive. Okay? So there you go. So that's going to work. So I've got a positive value and a negative value. So between these 2 points there has to exist another root. I guess I can call it D. Okay, so by the same reasoning, there exists a D in the interval from negative 10 to 0 such that f of D is 0. Like that. Everybody comfortable with that? Okay, that should be pretty quick and easy. It's just a little bit of trial and error to find positive and negative values, but beyond that, there's nothing too strange about that problem. Okay? Everybody good? Are we done? I've added a new twist. I think in the there were some homework problems where it just said show that there are at least two different roots. Clearly these roots are different because they don't exist in the same interval. But this one is a little bit more precise in that I want you to show that there are exactly 2 roots. So, does anybody have a suggestion how I'm going to do that? I have to show there's no more roots. We found 2 roots. There can't be any more than that. Ah, you're thinking about Rolle's theorem and the mean value theorem. What gets you thinking about that? Can you?
I remember doing in calculus.
Oh, you've done problems like this before.
Yeah, you assume that there's 3 real roots and then you
Okay.
use contradiction to show that.
Assume more than 2 real distinct roots. Now here's the thing, and this does rely on a little fact that's not part of real analysis, but really complex analysis. This polynomial cannot have exactly 3 real roots, because if that happened, then you would have to have exactly 1 complex root. You see, it's a 4th degree polynomial, and the fundamental theorem of algebra, which is not really part of this core material we're learning here, but the fundamental theorem of algebra says that a polynomial of degree n must have n roots. Now they could be repeated roots, they could be complex roots, they could be any kind of roots, but there must be exactly n of them. So there have to be 4 roots, but the thing about complex roots is they always come in conjugate pairs. You can only pick them up 2 at a time. So if a plus bi is a root of a polynomial, then so is a minus bi. And I can show, if you're interested in knowing more about why that's true and how it works, it's something I could show you very easily. But it's outside the scope of Math 350 per se. But my point is, you cannot have exactly 3 distinct real roots. So if we're assuming there are more than 2 of them, then we're actually saying that all 4 of those roots are real roots. Okay, so suppose we have 4 real distinct roots. Let me just call them R1 less than R2 less than R3 less than R4. So I can actually put these guys on a number line. Here's R1, here's R2, here's R3, here's R4. Okay? So you have 4 distinct real roots like that. Okay. So then kind of what you're doing is you're looking for a contradiction. And so Dominic suggested that we try and use Rolle's theorem. Can anybody else state Rolle's theorem for me real quick? Jason, do you know it? Don't know Rolle's theorem? But you will by Wednesday, right?
Yeah.
Okay, good. Ulysses, do you know it?
I know how to use it. I can't
How do you
cite
know how
it.
to use something you don't know what it is?
I used it like 30 minutes before
The session.
session started,
Okay.
but I cannot recite it by heart.
Can you tell me the gist of it then?
Okay. So, if f is differentiable between a and b, closed interval, and
Actually continuous.
and differential between a and b, which is an open interval.
Right.
If this is c in that open interval,
Mm-hmm.
such that f of c is equal to 0, but f of a has to equal to 0 and f of b has to equal to 0.
Okay, almost right. The derivative of the function is 0
Oh, that's right.
at that point in between.
Mm-hmm.
Yeah. So the function is continuous on a closed interval, which this will be, and differentiable on an open interval, which this will be for any intervals that we want to look at. So that part's all going to be clear and good. Then if I have 2 values where the function is 0, the endpoints of an interval, then somewhere between those 2 points, the derivative has to be 0. So does anybody have a proposal for what interval or intervals I should be playing with here? I've got the picture right here.
R1 and R4.
So I could go from R1 to R4, I could do that, and I'll know that somewhere between R1 and R4 the derivative is 0. But I won't know whether it's here, here, or here. So could I try something different?
You go R1 to R3 and then R3 to R4. Should
That's better. Now I'll be able to milk Rolle's theorem twice now. If I go from R1 to R3 and then from R3 to R4, I can milk it twice. But can I do even better than that?
Each one.
Yeah, how about just using each of them? Let's use each of them. Okay. That way we can get the most mileage. So in other words, the function has to be 0 somewhere there, somewhere in there, and again somewhere in there. And actually this is kind of looking like the general shape that you would expect, right? Okay, so there's going to be at least 3 different points, okay? So I'm just going to say applying Rolle's theorem to the interval R1, R2, R2, R3, and R3, R4, there exists a C1 in the open interval R1, R2, a C2 in the open interval R2, R3, and a C3 in the open interval R3, R4 with f prime of C1 equal to f prime of C2 equal to f prime of C3 equal to 0. So all of those derivatives are 0. Okay? So this is going to be C1, C2, and C3. Something like that. Okay. Is that a contradiction? What haven't we done yet that we probably should do? Yeah, take the derivative of the function, because if I don't take f prime of x, then I don't really have a way of thinking about this very well. So let's just compute the derivative. Note, f prime of x is, so what is the derivative of that function? Ask an easy question here.
4x cubed
Uh-huh.
plus 21x squared.
Plus 21x squared. Okay. And we're saying that that is 0 at 3 different points. C1, C2, and C3. I don't know where those points are, but 3 different values of C, we get a derivative of 0. Does that seem possible? Why would this function not be able to have 3 different points where it's 0? You can actually find the roots of this, right? If you just factor out the x squared, it leaves you with 4x plus 21, and you can clearly see that the roots are 0, 0, and 21 over 4. So you only get 2 different roots for the derivative, but yet here you said you had 3 different places where the derivative was 0. Okay? So, so f prime of x has only 2 roots, and that, of course, is a contradiction. That is a contradiction. Okay? The derivative has only 2 roots. So I like this problem a lot because it uses the chapter 4 material on the intermediate value theorem in the first part, and it uses the Rolle's theorem, which is just a special case of the mean value theorem, on the second part. The only thing about it is required is this sort of outside knowledge about complex roots coming in pairs. But beyond that, it's really a pretty good way to apply material from 2 different parts of the course. Yeah, Joseph?
And the reason that we had to do this with R4 is because the complex roots coming in pairs, right?
Right.
Because if we had done this, just suppose there's 3 of them, then we wouldn't have found that contradiction. But
Right.
then that contradiction would be that complex come in pairs, right?
Mm-hmm.
Alright, thank
Yeah,
you.
the
Just
complex
explain
root, yeah, the complex roots have to come in pairs. I need to think about this because I'm still not totally happy with this problem. The issue I have with this still is, okay, yes, there's more than, assume there's more than two real distinct roots. You could have four roots that are all real, but one of them got repeated twice, in which case you really only have three. So is that an issue? So that would be something like, so in other words, your graph could look something like this. 1, 2, 3 roots. And this one is a double. That's a root of multiplicity 2 right there. So then I don't have R1, R2, R3, and R4. I have R1, R2, and R3 equaling to R4. And they are all real, but one of them came up with multiplicity 2. And if that happened, then I can't create 3 intervals there. Might have to argue somehow that from some of this kind of stuff that you don't have this situation. So for example, I know that it goes from negative to positive right here, and then I know that at negative 10 it's positive again. So I know I've got a different root there. I might need to work a little harder to make sure that it crosses back over to the negative side so it doesn't just touch the axis but actually crosses it. So, and actually I don't think that's going to happen to the right of 2. It might actually have to happen somewhere in here. Is it possible for it to be positive at some other negative value before I get to? I have to think about this. This just hit me right now that you could have a double root. Yeah, once you get to the right of 2. Once you get to the right of 2, your derivative is always positive, so you know it's just going to keep going uphill. It's not going to come back down again. Let's see, the roots are at, so it's flat right here, and then it's also flat at negative 21 over 4, which is about negative 5 approximately.
Yeah.
So when we put in negative 5 into this thing, what do I get? I get 625. I get a negative number, so I'm still negative. Well, actually, wait a minute. This function only has 2 distinct real roots, so of course I'm not going to have it crossing over again.
Yeah, best case scenario, it would touch.
Well, how am I going to argue? How am I going to argue that this is not the right picture? I have no idea. I have to think about it a little bit. I think it's very doable, but I have to think about it. Do you have an idea?
Oh, do you want the numbers that we used yesterday?
No. I know we used maybe slightly different values, but yeah, I didn't bring this up yesterday. This issue that you could have one of your roots being like right where it was touching. So then this contradiction proof doesn't quite work. There's probably a good reason. I just need to think about it. So the derivative would be 0 twice. So here this would be 0. It would be flat right there. And this would be negative 21/4. It could be flat right there. Right? It not
But it would be flat the third time. Right at your
not according to the derivative here. It's only flat at 0 and negative 21.
But to have that, it would be.
Well, where else is it? Oh,
Right
it's,
where you touch.
oh, right here. Oh, it's
You don't
flat at one of the roots. Oh,
Yeah.
there you go. There you go. My derivative, the only places where the function is flat is at 0 and 21/4, and neither one of those is a root of the function.
Yeah.
So that means that whenever I'm at a root, my graph is actually crossing through the axis. It's got a non-zero slope. So therefore, it's got to actually cross through it, and then it can come back through it again, but now it's going to cross it. It has to cross it 2 more times. Okay. Everybody follow that? It helps to, but see, I would have needed to do this part first before I state that there's 4 real distinct roots. So, we're proving that there's exactly 2 distinct real roots. So you might have to explain, explain why aren't there 3 different roots? And then why aren't there 4 different roots? The 4 different roots case is this part. The 3 different roots is if there were 3 different roots, then the graph would have to have a root, and the derivative of the graph would have to have a root at the same point. And they don't, because we know exactly where the derivative's roots are. They are 0 and 21/4, negative 21/4, sorry. 0 and negative 21/4, which are not roots of this. I can just about guarantee you if you, well, we know already. Plug them in there, you're not going to get 0. Okay, so that's a little bit more precise. You okay with that? I spent way more time on that than I wanted to, but it's still a good problem. You have to be able to factor the derivative though too, right? You come up with some cubic derivative here that you don't know how to find the roots of, then you've got a problem. So, okay, let's move on. I'm going to skip number 5 because it's very similar to the mean value theorem. It's kind of a generalization of it, and I don't think that there's really a lot more to be gleaned from that right now. So you guys can try that on your own if you want and peek at my solutions later. Let's go on to number 6. Number 6 says, suppose f is continuous on closed interval AB and diffable on open interval AB. Prove there exists a C in the open interval AB such that f prime of C is equal to b squared f of b minus a squared f of a all over c squared times the quantity b minus a minus 2f of c over c. Okay? Anybody have any... When you see something like that, does anything spring to mind of the material we've been doing recently? Looks a little bit like the mean value theorem. Just even the assumptions. It's continuous on the closed interval AB, differentiable on the open interval AB. That's often the assumptions that we've been using. So the mean value theorem says what? Can you remind us, Dom? This is another one you need to know by Wednesday. Mean value theorem statement.
If we have those 2 conditions continuous on the closed interval, differentiable on the open interval, then there's just a C in the open interval such that f prime of C equals f of b minus f of a over b minus a.
Okay, perfect. So this is the, with all the assumptions in place, this is the conclusion, right? So there exists a C, and notice the C is even existing where we want it to exist, right? So it does look set up pretty well for it. It's just, this doesn't look like the mean value theorem. It's more complex. So the question becomes, how can we use this if it's not that? so this function started off with some f, or this problem started off with some function f, we don't know what it is, right? And we want to prove this thing about f. And then we came over here and we wrote down the mean value theorem, and we used f again, as if this f is going to be the same f as that. I'm going to do something that I hope will be actually helpful here, which is I'm going to change the notation just so you don't start thinking it's the same function on both sides. So if there's maybe some other function g that it still has, this function, whatever it is, has to still be continuous and differentiable in the right places, but we could apply this to some other function. Does anybody ring any bells or help anybody see what to do? This is an example of a problem. You don't want to try and figure out the whole thing right now in your head. You just want to think of a possible way to go with it, and then we'll try it out and see. Because this is too complicated to sort of somehow figure it out from algebra quickly. You can't do that. You're going to have to let the proof come to you after you get the strategy going. What I'm saying is, don't apply the mean value theorem to the original f. Apply it to something else. Is there something else that you, just looking at the form of what you have in the box on the left side there, is there another function you could apply this to? Is there a g of x that we could explore? There is.
Would you just explore your f of c?
Say again?
Your f of c.
F of c. Not sure what you mean. Hey there. You want to hang out?
Yeah.
Go ahead. This comes under the heading of I can tell you what the answer is, but then it's sort of you either see it or you don't, and if I just tell you the answer, then everything's boring. Let me give you another minute or two to stare at that before I spill the beans. It's actually not that. I don't think it's. I think you should be able to come up with this. I'll put it that way. I'm looking for a function that you could apply this theorem to, other than just f of x, because f of x gives you that, it doesn't give you what you want over there. But by looking at what you have over there, you might be able to see a function that we should use. And I don't want you to do any algebra to this to come up with it. Just looking at straight what you've got right there is the best form to see it in.